Hello kids, today I will be doing some topical questions from past papers for the unit properties of waves to conclude this unit for you guys. So let's get into it. So here's the first question. Let me just turn on my pen to scribble. Right, okay. Now if you look into this, the question is asking figure 6.1 shows the wavefronts. Now we do know wavefronts are straight lines. These are the wavefronts. Please don't mind because this presentation tool is not accurate for my graphics pad, so the lines are not going to be as straight as they're supposed to be. Approach a gap in the barrier. Right now, I gave you this rule that if lambda, the wavelength, is equal to d, then we get circular pattern, right? So for this, let's draw a circular pattern. I hope I can make some shapes, lines. Okay, and okay, we don't have the shapes. Okay, let's stick to the scribbling. So what is, draw three wavefronts to the right of the barrier. So I'm just going to draw a circular wave pattern. Now remember to maintain the wavelength distance, this gap, right? The wavelength, which is the lambda, and this is actually d over here, right? So this is actually lambda again. So try to maintain the same lambda when you're drawing this. Use a proper set square and draw very neatly. So these are the three wavefronts you will get. So one mark is for the three wavefronts, and one mark is for keeping this lambda as the same as this wavefront. So this is the solution for the first question. Let's into the second part. What if the gap is increased by 5 times? Now we do know if d is greater than lambda, then we only get edge diffractions, and also need to understand that the wavelength is small. We do know when the wavelength is small, then there is very little diffraction. I'm just giving these dotted patterns, right? So we are going to get straight wavefronts in the middle, right? I'm just going to dot it out as well. So just simply draw out a dotted line for your own sake with a pencil, that these part of the wavefronts are going to be straight, and then simply round them up a little bit from the edge, right? So this is the diffraction that you will get in this case, right? Simple edge diffraction. And we do know if the wavelength is large, then this angle is supposed to be much higher. If the wavelength were large, then we would have drawn these round edges to this point, right? To this. For large lambda, and this much is for small lambda, right? So keep that in mind. This is how we're going to solve this, right? So this is the solution for these three wavefronts. Again, 1 point for the wavefronts, accuracy of the wavefronts, and second is for keeping the lambda same as this one, right? It should be the same. Moving on. Describe with a label diagram an experiment using water waves that shows the reflection of a wave that occurs in a straight barrier. So I'm going to use this straight line. So I'm just going to draw, let's say if we've got this vertical this barrier, right? I'm going to change the color to blue to depict what the wavefront are supposed to be like, right? One wavefront, second wavefront, third. So draw some wavefronts like this, and simply now draw a vector. I'm going to draw a black vector to represent where it is supposed to be going, right? Like this. Okay, now this is how this is going to look like, and where it is going to change its angle, I'm going to draw the normal using this line. Let's say if this is the normal, right? So from the normal, again it will move to the other one. So I'm going to draw this black line again, where the direction vector is going to be, right? The angle is supposed to be the same. I'll draw in a moment. So I'm going to draw this. I will complete this diagram just in a moment. So this is how the wavefronts are going to go after reflection, right? So this is how the wave is going to be. Ensure that your gap between the wavefronts is the same, right? Now I'm going to use the pen to draw rest of the you know, possibilities. Okay, now over here, okay, let me get this black, right? Okay, now over here, this is where the wave is going to be, right? And you're going to note this as theta I, which is the incident angle, and this as theta R. We do know that in reflection, theta I is equal to theta R. That means the angle at which these wavefronts are incident should be equal to the angle at which they are reflected. Now this can be drawn at several angles for this barrier, right? This is the barrier, so do label this so that there's no confusion. This is the normal, right, to this surface, which will help you draw these angles. Draw these angles using protector. You can call this as reflected waves, right? And these ones as we call them as incident waves, the waves which are incident on these barriers. So once you label this properly, then there's very little description that you will be needing to write this, right? So I'm just going to try and write this. I'll instead use if there's a possibility of writing something, laser pen magnifier. Okay, let's use, you know, the scribbling to write this down. So now it is saying, as experiment shows. Now simply describe this experiment. We can simply describe this as like waves incident on barrier would be reflected at same angle to normal of barrier as of its incident angle, right? So this makes it very easy. I didn't write much. Why? Because my diagram is very much explanatory. So keep that in mind. If you draw a beautiful diagram like this, if you label it properly, if you give this side information like this, just simply highlight it using a pencil or something, just draw it on one side. As I said, my scribbling for this presentation tool is not good enough. It's not detecting much of you know, the writing very easily, unlike the, you know, MS Notebook. So just go with this, right? So this will this won't require much of the description. You just simply have to write the waves incident on the barrier would be reflected at same angle to the normal, which is this normal line of the barrier as of its incident angle. Sorry, I missed the word angle over here, right? So once you write this, simply write this over here, theta I is equal to theta R, just to reinforce this rule over here, right? And once you do that, you will get 4 marks as a whole, right? And probably 2 marks for the diagram and 2 marks for the description, right? So keep that in mind, the marking scheme. Got it? Moving on, encircle 2 of the following that apply. 2 of the following that apply to an ultrasound. Now we haven't discussed ultrasound yet, but we will be soon discussing this in the classroom. So we do know that ultrasound actually is a sound. Human audible range is 20 hertz to 20,000 hertz, right? That's the human audible range. And ultra means something which is greater. So ultra will be here, right? Ultra after this. So ultrasound should have a frequency which is not over here, not over here. So this could be the frequency that is there. That could be 1. We can donate to as ultrasound because we are supposedly discussing ultrasound. Now we have an option for longitudinal, which we do know that ultrasound is a sound wave, so sound waves are longitudinal waves, but I'm not going to highlight it at the moment. Transverse is not a possibility. Again, speed, we do know for speed we use the formula v is equal to f lambda. Now we do have a certain value for frequency from here, right? This is f, but where is lambda? So we don't have lambda over here, right? So since we don't have lambda, so we cannot calculate speed in any way, right? So we're just going to cross these three speeds and simply highlight these two options. These are the two correct ones, so that will solve you, right? So 1 mark for this, 1 mark for this, 2 marks cured. Okay, calculate the wavelength in a vacuum of X-rays. Now we do know, we haven't discussed this because this we will be discussing in IG 2, since we will discuss it from light. As I said, when we go for topical past paper, they actually have structured questions which refer to several units altogether instead of just focusing on one unit as a whole, because that way the questions will be very limited. So I'm just going to write the speed, which is actually 3 into 10 raised to power 8 meter per second. That's the speed of light or any electromagnetic radiation. This is the EM wave, right? So electromagnetic waves, they all have same speed, which is represented by c, right? Speed, I'm just going to write it over here, speed of light, right? That is same for vacuum in every object, which is this. So we do know v is equal to f lambda. We have the value for f, right? We want to calculate lambda over here, unknown. So we have the value for this, so just put lambda over here. So it is going to be v by f, which is going to be 3 into 10 is to power 8 divided by 1.3 into 10 is to power 17, and that is going to be a large negative number. So once we write this down, let me just pull up my calculator to calculate this. The answer is going to be 3 divided by 1.3, which is going to be over here 2.31. As I've rounded off, it's 0.7. I've rounded off to this, multiplied by 10 to the power minus 11, and this, since it's in hertz and this is in meter per second, so the unit is going to be meters. So 1 mark for working, 1 mark for unit, and 1 mark for your answer, right? So 3 marks over here. So again, I will reinforce the idea that you need to understand the marking scheme. Whatever the marks are given, you have to consider that as an important factor while writing your answer. So do show your working. I've seen a lot of students who don't show the working, just simply write the answer, and then they expect to get all 3 marks. That's not possible, because there's 1 mark for the working that you have to show, which is like the importance of this formula. If you don't write the formula, don't expect to get that 1 extra mark, because that's mandatory. Then 1 mark for the accuracy, which is again 3 significant figures, which I always reinforce. Your answer should have 3 significant figures, which is this, and then the correct unit, which will also award you 1 mark for this, right? Okay, moving on. A dentist takes x-rays, x-ray photographs of teeth. Explain why it is safe for the patient to be closer to the source of x-rays, but the dentist must stand away from the source. Now you do understand that X-rays bounce off from material, harder material. Now this is from the unit radiation, so I'm not going to discuss this question as of now. State why 2 reasons microwaves are designed. Again, I'm not going to discuss this because this is coming from the unit light. So we haven't discussed this, and we won't be discussing it for this year. So I'm just going to skip forward. Again, it's a part of the same question from one paper. I've taken these questions from past papers as a whole instead of taking it in parts. So now let's come to the next question. Sound is a longitudinal wave. Sketch a representation of longitudinal wave on your sketch. Indicate the wavelength between these 2 points, and mark label compression and mark rarefaction. So I'm just going to get to line, right? So I'm just going to draw 1, 2, 3, and 4 wave fronts, right? And then I'm going to draw a compression, which is going to be 1, 2, 3, and 4, right? and then we have again a rare fraction which is like farther apart from one another. So this is how it is supposed to look like, right? So and again I'm going to create a compression over here. So again a compression. Draw this very neatly because you will have to answer these 3 points, right? So your neatness would really come into effect. If it's not neat, then it is going to be some trouble for you, right? So again we're going to have this larger wavefront over here, and then we can mark the centers to evaluate the refraction and the compressions, right? Now it does appear to be expanding a little bit, right? There you go. Okay, to now mark the centers, now I'm going to use this scribbling tool. Let's get back. One point is this, I'm just going to mark, and the other is like this, the center of it, right? So that is C and C, and I'm just going to draw this gap that this is lambda, right? And another one, rare fraction from here to here in the middle, this is also going to be uh, R and R, and that is going to be lambda. Now in my diagram, as you can see, the space has varied a little bit, so make sure that the lambda, this and this is actually the same. For my diagram it appears to be a little different, but technically these are, if you look at this, so this and this appear to be pretty much close to one another, although there's some error in my drawing. So make sure that these lambdas are equal. If they're not, then you're going to lose 1 mark in the diagram for wavelength. So wavelength is represented, compression is represented, and rare fraction is represented. So 1 plus 1 plus 1. So actually the diagram itself has no marks, but these representations are important, and that is only possible if your diagram is correct. Only then you can score these 3 marks. Then if the diagram is not accurately drawn, just like mine, you are going to lose all 3 marks. Since I'm using this digital tool, so it is obviously, I don't have a ruler over here to draw these neatly, right? So ensure that you're using a proper ruler to draw these lines and keep this gap very, very accurately drawn, right? The better strategy would be to mark 2 points altogether first, and then draw 2 compression lines here and then here, and then draw the rare fractions between them. Just draw these 2 points, take any 2 points, then also take 2 more points like this, and ensure that these 2 points and these 2 points are at equal distances, and then you can draw these rare fractions, right? Okay, descriptive questions. Again, over here, a longitudinal wave. Now remember, it's a longitudinal wave, right? A longitudinal wave, which are p-type waves, right? We also call them as p-type waves or parallel waves, in which the wave is propagating forward, and the particles are also moving parallel back and forth. Direction is the same as that of the direction of the wave into one medium to another medium, right? Since the medium is changing, one medium to another, the speed of the wave is slower in the second medium. If the speed is slower, then what will happen? Now I did discuss this in class, that frequency does not change. So for any case, the frequency does not change, because the energy can neither be destroyed nor be created. So frequency is a representative of energy, so energy does not change, so the frequency won't change. So what will happen to the wavelength? Since the wave is going slower, then the wavelength has to be longer, right? It would become longer than before. So let's say if a wave was going like this, then this is faster, then it should go like this, right? This is fast and this is slow. So apparently the wavelength is now longer, keeping the frequency the same. So this is what is the difference, right? Okay. State the typical value of speed of sound in air. The typical values actually range from 330 to 340 meters per second. Still, we haven't discussed this in class, but you will be going through this in the subsequent topic. So let's solve. I'm just giving you this value that it is from 330 to 340, and why it's a range. I'm not giving one specific value. Typical value, I mean, you can write the range and you can get 1 mark. You can write any number between 330 to 340 and it will be correct. Let's say if you write 336, so that would be also correct, right? Any number between this range would be fine. Why? Because the temperature and the density of the air affects the speed at which the sound is traveling through air. So in different conditions, the speed of sound is different. In hotter temperatures, the speed of sound is faster. In colder temperatures, the speed of sound is slower. Why? Because the particles are much more sluggish at colliding with one another. When they're energized, they deliver sound much more faster. So moving on, again, a student has drawn an attempt to show the diffraction pattern. This is now diffraction, right, of water waves that have passed through a narrow gap. Now we do know that this is gap D and this is wavelength, right? Since apparently appears to be closer to D, right? What are the state two things which are wrong in the wave pattern that is shown? Number one is, as you can see, the wavelength is dramatically changing, which, if you recall, in the first question I told you that the wavelength must be kept constant, otherwise you will lose marks. So this is what the student has done wrong. So we can say the first thing which is clearly visible is wavelength is changing, so that's wrong, right? That's the first thing is wrong, which is wrong about this. And secondly, he has drawn a linear wavefront, right? Linear wavefront instead of circular, right? So if I were to draw this correctly, then I'm going to use this orange color. It should have been something like this, keeping the wavelength the same as given by this. So this is how this should have been, right? This is the correct way, right, to draw this. This, however, is wrong, right? The question has already stated that what is wrong, so you don't need to give the corrections over here. You just need to identify what was wrong, which is wavelength is changing, which is wrong. Linear wavefronts, which is also wrong. It should have been circular. So just write these two and you will get 2 marks for this. Moving on to the next part of this, in the space below, sketch the wave pattern. The gap is 5 times wider, right? Now let me draw a shape over here, right, to draw the barrier. So if the barrier is 5 times the wavelength, just measure how much it is in terms of centimeters and then give that pattern. And now I'm going to draw the angle. I'm going to use a different color over here. First, just draw a linear pattern from here like this as a soft line so that you may erase it later on, right? This will help us identify the straight wave pattern. And since the wavelength is small over here, right, I will draw these in a moment and explain. Now this I'm going to use as a smaller angle, right, like this, so that I have a neater diagram this time around, unlike the one I sketched before using the scribbler. Now let me draw the wavefronts. Now this is how the wavefronts are going to look like. Initially, I'm going to try to keep the lambda as same as possible as in the given diagram. I'm going to draw several fronts so that it's clarified to you. I just explained that if the wavelength is small, then there is very little diffraction, edge diffraction this is called, right? There will be very little edge diffraction that you're going to experience in this. If the wavelength is larger, then the edge diffraction is actually larger, right? So now I'm going to draw these circular edges, right? Oh, okay. So this is going to alright, I need this scribbling. There you go. Sorry for that. It is actually supposed to be a bit circular like this. So circular, circular, circular. Just join it with the blue line and then erase this blue line, and this is how the pattern is going to be a bit circular from here. So this is edge diffraction. This is called edge diffraction, right? So this is what you're going to get. Now also the wave approaches the barrier with a wavelength. Now this is wavelength and a frequency which is now f, right? Calculate the speed. We do know v is equal to f lambda, so do show it in your working. So v is equal to f lambda, right? V is equal to, we need to calculate the speed, which is v, right? So v is equal to f lambda, the frequency is 8, the wavelength is 1.2 centimeter. So just multiply this and give the answer in centimeter per seconds. Now if you want to go with meter per second, then you'll have to convert this unit, but since it is already, the wavelength is in centimeters, so just go with the same unit as that of provided with the wavelength. The speed will have a similar unit as of the wavelength and frequency, and frequency is usually expressed in terms of seconds since it is hertz. The unit for frequency is always hertz, either megahertz or kilohertz, but still in hertz, so you will go with seconds always. But the unit for the distance can be changed. So let me just pull my calculator. So it is going to be 1.2 into 8, so that is 9.6. Yes, so the answer is going to be 9.60. Again, three significant figures. Why I place this 0 over here is explained in the video where I've explained significant figures and scientific notations. So again, scientifically corrected number, so you will get 2 marks, right? One for the solution perhaps, and one for the whole answer and the unit. Got it? Last one over here shows a scale drawing of a plane waves approaching a gap. We do know that this d and this is lambda, and since d is nearly equal to lambda, so we're going to have a circular pattern. Draw the pattern at which we're going to get this. So I'm just going to use a different color now. It is going to be like this. Keep the wavelength similar to that of given in the diagram. Ensure that your lambda is the same, right? So sorry, yeah, we have to keep the lambda same, so I'm trying to draw as neatly as possible. So ensure that lambda here and here should be same lambda, right? Keep that in mind, and once you do this, this is correct. Simply label this you will say as circular wavefront, right? And this lambda being drawn over here will give you this, right? So this is this. Now second part, waves approaching the barrier is of wavelength 2.5. This is lambda with the speed which is v. Calculate the frequency f, right? So again, v is equal to f lambda, and since they have given you this space over here, once there's a lot of space, understand you have to show the working, right? So I will say always show working. I would recommend, even if the space is little, try to work very neatly in a smaller space, but do show your working, whatever you're calculating, because that would give you an edge. In case if your answer is wrong, you would at least get 1 mark for the working or writing the formula, right? So the wave speed is 20, right, which is in centimeter. Now remember, you have to match the units for wavelength and speed. Since they are same, so we can actually multiply and divide them. If the units are not same, then you have to convert the units of wavelength to that of the speed so that they can be multiplied. If the units are not same, that do not multiply or divide those numbers, the answer will always be inaccurate, right? So it is going to be 20 into frequency into the wavelength, which is 2.5. So frequency is going to be 20 divided by 2.5, that is going to be 8.00 hertz. Again, look at this. This is 3 significant figures. keep that in mind. So I've added these two zeros. Why I added these two of the zeros, you need to understand that this was in decimal, and this was also a two digit, so I need to at least have one zero to collaborate with this decimal fraction of the wavelength. But nonetheless, we require three significant figures, so it's a whole number answer, which is 8 purely, doesn't have anything at the decimal point. So I will just add these two zeros to signify three significant figures. We do know this rule that zeros after the significant figures are also significant, so these will be added to your significant figures and make your answer correct, right? Okay, state the frequency of the diffracted waves, right? What is the frequency of the diffracted wave? Uh, what happens to the frequency? Now by state it means what happened to the frequency. Over here we're going to say unchanged, right? The frequency does not change after changes in the wave speed or wavelength, right? That does not change. If it were 8 hertz before, so that would also be that is 8 hertz even after uh, diffraction. So this was before, and this is after. So keep in mind the frequency does not change, so it will also be the same. So if you write this unchanged, that is this, so this will ensure that the examiner gets your point. Why have you written this 8 hertz, right? Okay, I think that's it for these questions. This question session. Once I will find more troubling questions. These were some of the few questions that are commonly found. So if you have any queries, if you have any lack of understanding, just post it in the comments. I'll try to respond as soon as possible, and post a video or answer in the comments. Thank you for your time. Bye bye.